Hello, everybody. Thank you for giving me the opportunity to present here in Green Conservation Conference. I'm Sathiyanarayanan from the Institute of Chemistry, University of Neuchâtel, Switzerland. I'm going to present one of our current project called Microbes for the Archaeological Wood Conservation. So currently, most of the archaeological wood discoveries consist of waterlogged archaeological woods, which means wooden objects have been waterlogged for centuries, and these waterlogged archaeological woods can provide valuable information about past civilizations. First, we must look when the wood is still under water, especially in seawater or in lake, for example. In this condition, the iron parts of the wooden object tend to corrode, which release iron ions. These ferrous ions reacts with the sulfide that comes from the reduction of sulfate from the environment by sulfate reducing bacteria, which result in the iron sulfide that precipitate and accumulate within the wooden object. At this stage, degradation may occur different organisms, but mainly bacteria, when there is no oxygen or at low salinity. In particular, the presence of wood-degrading bacteria increase the fragility of wood structure by consuming the cellulosic compounds, and bacteria also that cause the precipitation of organosulfur compounds and iron sulfides. However, the main issues occurs after the excavation, especially the presence of acids and salts that recovered in wooden objects. During the excavation or after, wooden object will get exposed to the oxygen, especially the oxygen environment and relative humidity, which enhance the oxidation of iron sulfides, which producing the salts and acids that can damage the wooden object, which lead to the total loss of the material. Moreover, the presence of iron ions can degrade the wood by a production of oxygen radicals. In fact, iron sulfides that formed previously tend to oxidize, and acidification process that takes place leading to the formation of sulfuric acid. Salt precipitation then follows, causing the formation of substances up to 3 times larger volumes. Basically, the volume of substances increases the cracks and efflorescence, and short of decrease the strength of the structure. Therefore, in the long-term perspective, extraction of iron sulfur species is highly essential for the stabilization of recovered waterlogged archaeological woods. So after the discovery of wooden objects, the artifact is often recovered and consolidated. Currently, different methods are being employed for the conservation. The first procedure is consolidation of the recovered wood. The consolidation is mainly based on the impregnation, especially the polyethylene glycol is commonly used to remove the water from the waterlogged archaeological wood. Some other products such as polysaccharides and alcohol ether solution are also used for the consolidations. Following the impregnation, in order to avoid the issue of sulfur and iron byproducts, as I mentioned before, the different curative or extraction methods are being used on already consolidated wood. And these methods are remediating the sulfuric acids and extracting the iron sulfide. Currently, the chemical extraction and the deacidification or neutralization process are being employed. Most of them are having some disadvantages, also due to environmental concern. Therefore, the biological approaches are highly inevitable. Our preliminary study strongly suggested that the microorganisms can be used to extract the sulfur from the wooden object. Therefore, we propose a 2-step biological extraction method. First, iron chelating microbial secondary metabolites such as siderophores can be used to remove the iron from the wood analogs. Secondly, the sulfur oxidizing bacteria can be used to remove the sulfur from the same wood analogs. So we also validated our preliminary results with the synchrotron measurements, which confirm the effective oxidation of sulfur into sulfate. So we have evaluated our biological treatment approach on different species of wood models, such as balsa, oak, and pine, and also archaeological wooden samples that comes from different ages with a different state of degradation and contamination. We also screened various microorganisms and their secondary metabolites, such as pyoverdine from Pseudomonas foetida and deferoxamine from Streptomyces pilosus were used to extract the iron from the wood samples, for example, balsa, oak, and pine. Siderophore that comes from the Streptomyces pilosus, such as deferoxamine, had shown the highest iron removal rate and also comparable with the chemical iron chelators such as EDTA. For removal of sulfur, thiobacillus denitrificans was chosen since it is an autotrophic and facultative anaerobe and it doesn't utilize any organic carbon source. Therefore, this bacterium is completely safe to use on the wooden artifacts. As I mentioned before, we have developed a two-step biological treatment to remove the iron and the sulfur, especially iron is being removed using siderophore deferoxamine, and then later sulfur is being oxidized using thiobacillus denitrificans. Biological treatment also compared with the chemical treatment that also performed in two steps, where sulfur is oxidized by sodium persulfate and then iron is complexed by EDTA. And both biological and chemical treatment is compared with the untreatment, which has only deionized water instead of biological or chemical treatment components. So while coming to the results, so after the course of treatment, the visual appearance of the cubes clearly revealed that chemically treatment has stronger visual aspects when compared to biological treatments. However, biologically treated samples were also more or less similar to the chemically treated samples. This was confirmed by color variation between before and after the extraction. Still, the biological treatment also visual changes, which might be due to the removal of iron from the wood analogs. After the biological treatment, most of the sulfur species were removed while studying the wood samples under Raman spectroscopic analysis. We believe that siderophore treatment extract the maximum amount of iron and remaining sulfur can be further oxidized by bacteria. And elemental sulfur was still detected in chemically treated samples, and especially the mechanoite and elemental sulfur were both detected in non-treated samples. To further confirm the iron and sulfur extraction, the quantification of iron and sulfur have been performed using ICP analysis, which revealed that the removal of iron and sulfur about 70% from the biologically treated wooden objects, especially the wooden samples. Overall, ICP analysis has shown the chemical treatment is more effective. However, our target is to find the environment-friendly, greener process to conserve the archaeological wooden objects. Therefore, biological treatment should be highly considered even if it has low efficiency in order to protect the recovered archaeological wood and the environment. Finally, the infrared analysis helped us to study the effects of the treatment in the wood substrate. As we know, wood is made up of lignin and cellulose and hemicellulose. Usually, lignin is more resistant than cellulose and hemicellulose. Therefore, we use lignin signals as a reference to detect the degradations. We observed that there is no difference observed before and after the biological treatments, especially are also untreated samples, which strongly suggests that the compatibility and efficacy of the biological treatment on the wooden models. Both biologically and chemically treated samples were consolidated using polyethylene glycol, and then we freeze-dried to check the compatibility of our developed protocols. And moreover, the artificial aging studies were also conducted to study the long-term stability of the developed treatment. So while comparing the biologically treatment and chemically treated samples, which shown the promising results, especially in the biological treatment in the aspect of appearance and inoculants and salt extraction and compatibility, while comparing with the currently used chemical treatment for waterlogged archaeological wood conservations. So we conclude that the combination of iron chelators and sulfur oxidizing bacteria can be used to remove the iron sulfide from the waterlogged archaeological wood. Currently, we are trying to reduce the overall cost of the treatment process, and also we are optimizing the oxidation experiment, especially using some aerobic bacteria, since we have used some facultative anaerobic bacteria such as thiobacillus denitrificans. So therefore, in order to simplify the protocols where we are trying to use the aerobic bacteria and also to increase the oxidation potential. So, and with this, I would like to conclude and thank you for your attention. And if any, I will be glad to answer your questions, and thank you all.